My name is Mark Coley, and I do Radiology and Informatics at Indiana University. Today we're going to talk about what I call patient-centric workflow, which is really an introduction to how informatics supports the generation of images and reports for any particular patient. So the two underlying technologies that we're going to focus on today are HL7 and DICOM. HL7 are little messages that are exchanged between servers, and I think of them like a specialized email. DICOM is the format that wraps images that allows us to exchange them in a standardized fashion. It also specifies some network operations and things like that. So this is the diagram that we're going to be focusing on for most of the talk today, and I just wanted to point out a few of the pieces and parts so that you can be able to follow along. So first we have our EMR, or our electronic medical record, over here in the upper left-hand corner. We have our critical results system. If you use critical results tracking like we do, this system is going to be one of the ancillary systems that's important for the workflow. Over here you have the laboratory information system. This I think was a missed opportunity. I think it really should be called a pathology information system, but that's a joke for another day. Over here you have the radiology information system, or the RIS. You have the PACS system, which stores images. Our ultrasound modality over here. Here in Indiana, we have a health information exchange. So this is another entity that will need to be connected and receive orders and reports and other information. And then finally, over here on the left-hand side, you can see we have our voice recognition system, or our speech recognition system, so that our radiologists can generate dictations. And in the middle, tying all of these together, we have what's called an interface engine. And I think of an interface engine like I do a router at home. It gets messages and decides where to send them, make sure that they go to the appropriate place. So as we go through this diagram today, what we're going to be doing is following Rex. Rex is an elephant, and he's pictured here on your screen. Rex has an unfortunate problem in that he has some right upper quadrant pain. And so Rex visits his doctor, and his doctor says, well, you might have gallstones, so let's go ahead and get a right upper quadrant ultrasound to see if that's the issue. So Dr. Bob writes out an order for Rex and basically hands it to him. So Rex comes to our imaging facility, and the first place that Rex goes, even before he comes in to the imaging department, is that he goes to registration. At the registration desk, they're going to do things like take down Rex's demographic information. They're going to assign him a medical record number. They're going to take any insurance information that he might have so that we can get paid for what we do. And in our particular environment, we enter all of this information into the electronic medical record, and that the electronic medical record then spits out what's called an HL7 ADT message. This stands for admission, discharge, and transfer. So that HL7 ADT message is sent out from the electronic medical record into the interface engine, and is basically distributed to all of the downstream systems after that. So now, with just one event, all of the downstream systems know that Rex is here. They know that what his medical record number is. They know what his insurance information is, and everyone is kind of kept in the loop. So this is an example of an HL7 ADT message. You can see here that HL7 messages are made up of several lines. Each line in the HL7 message is called a segment, and you can see here that I've highlighted the beginning of the segments over here on the left. So each one of these segments has a specific function. The first one here is the message header, or MSH segment. That one's present no matter what type of HL7 message it is. This tells you things like where it's originated, what the destination system is. It gives you a timestamp. Over here you can see that there is it's telling you that this is an ADT A04 message. And then there are other things like the name, medical record number, next of kin, and then other things about the visit. as well as the insurance information. And you can see that Rex is a self-pay. So these are just a couple of drill downs here. Again, you can see the message header segment. It says that this is the ADT outbound feed. Again, this is an ADT type of message, timestamp here. In the PID segment, this stands for patient identification. You can see that we have medical record numbers, not just for our zoo hospital where Rex is, but also for one of our other hospitals in town. And then you can see things like dates of birth, telephone numbers, those types of things are included in the PID segment. PV1 segments stand for patient visit 1. So these information that's specific to this particular visit. So you can see this message. I didn't quite scrub this out for Rex, but this was originally an emergency medicine message. So in addition to just registration events, ADT messages can also be communicated to, can also be used to communicate multiple other types of events. So say for instance, Rex comes in another time and gets assigned a second medical record number. You could issue an ADT merge that would take the old patient record and the new patient record and merge them together under the new good medical record number. Because you can imagine the situation that you would be in if you've got all of those downstream systems on the diagram, and a medical record number change would need to be updated in each one of those by hand. It becomes unsustainable quite quickly. So other types of messages that are common in radiology, HL7 messages, are order messages, they're ORM messages, and result messages. This is where your reports are going to be. In radiology, our result is a report. So this is an order results unsolicited, or ORU message. And we'll talk about each of those as we go along. I wanted to take a little break here and tell you that this is what we've been talking about so far in regards to HL7 are really HL7 version 2 messages. And those are affectionately known as pipe and hat messages because the fields are separated in any one segment. The fields are separated by pipe characters, and then subfields are separated by carets or hats. So this is HL7 version 2. And the reason why I point this out is because HL7 version 2 is much different than HL7 version 3. Version 3 HL7 is all based on an XML schema, and so you can see that the messages look completely different. XML tends to be much more readable. You can identify that the administrative gender code for this particular patient is female, and the birth time value is given here. Whereas if you look at the version 2 message, you have to know that you would need to look at the patient ID segment and then find the patient's birth date somewhere within that. So that's one of the advantages of version 3. However, I will tell you that for the large majority of production interfaces in any given clinical environment today, the majority are version 2. And that's because, as you can see, the messages are completely different, and so they're not compatible, much like USB and HL7 version, or sorry, USB 3.0 and USB 2.0 might be. This is a small screenshot. It's an old screenshot. It's confusing, but this is basically identifying the structure and the types of elements that can be included in an HL7 version 3 message. And really the take-home point from this slide is that it's incredibly complicated and next to no one understands it, which is one of the other reasons why HL7 version 3 has not been widely adopted. So as I mentioned, with USB version 2 and version 3, everything's happy, everything works together, whereas with HL7 version 2 and version 3 do not play nicely together. So heading back to Rex, the next place that Rex is going to go is the check-in desk for the radiology department. At the check-in desk, he's going to show the clerk his order. Again, he's here for a right upper quadrant ultrasound, and the indication's right upper quadrant pain. We're also going to capture who the referring physician is. All of this information is going to be collected and entered into the radiology information system. The examination will be assigned an accession number, a procedure code, and a procedure description. And the Radiology Information System, or the RIS, will take all of that information and smash it together into an HL7 ORM message. That ORM message is going to be sent out through the interface engine again. Remember, this is the router that sits in the middle where and sends messages off to the systems that need to know about them. And for us, the EMR doesn't necessarily need to know that what the accession number is for this particular examination. But our voice recognition system, and certainly our PACS, and also our critical results system needs to know that Rex is here and what he's here for this particular order. So this is an example of an HL7 order message. You can see that again it's made up of multiple segments. We again start with a message header that identifies the message type as an ORM. And then you can see that we have specific information about the order. In this schema, this right here is the accession number. So 3011038 is the accession number. And here you can see this is an OBR segment, which is an observation request. Again, it says that we have the accession number. It indicates here this is our procedure code, US 11759. And then the procedure description is ultrasound right upper quadrant. You can see that this also includes the indication of right upper quadrant pain and indicates the ordering physician here. So the next step is that Rex goes into the procedure room where the technologist is getting ready to set up the ultrasound machine. The ultrasound machine communicates with the PACS system through a DICOM operation called DICOM modality work list. And essentially what the ultrasound machine is doing is requesting a list of all of the patients that need to be done that day. So here you can see is a picture of our ultrasound machine, and you can see a list of all of the exams, the patient's names and the ID numbers and accession numbers and study descriptions are all here. So the basic demographics are already available. Here's Rex's. So when the technologist clicks on this particular line, it's going to populate the scanner with the information that we got originally from the Radiology Information System, but through the PACS via modality work list. So Rex is getting his ultrasound performed. Technologist is acquiring multiple images, and so there you go. So there are a few ultrasound pictures from Rex's ultrasound. I wanted to take a little bit of a break here and talk to you about DICOM. So DICOM is a very, very technical standard, and it's huge. It not only specifies the way that images are to be represented, it also specifies network operations for exchanging images. It specifies things like we talked about with the DICOM modality work list and many, many, many other things. The standard is actually reasonably readable for normal humans, but finding the information that you want can be really challenging. So I'd encourage you to take a peek at the DICOM webpage, but make sure that you have use the find function in your PDF for whatever in your PDF viewer for whatever you might download from here. This is just another screenshot that shows you all of the different parts of the DICOM standard. There are many, many, many bits and pieces, and it's very complicated. But like I said, it's actually fairly readable if you do download pieces and parts of it. All right. So I wanted to talk briefly about metadata. Metadata is a term that we throw around a lot, but you may not be familiar with it. And so this is a digital picture that I took when I was in Italy. And the types, basically all digital pictures nowadays have metadata associated with them. So common metadata about this picture would be things like the camera that I used, what the aperture and focal length settings were, the exposure time, any software that I may have used to process the picture since then, and so on and so forth. When it comes to a medical image, the metadata that you're going to have is going to include things like when was the study acquired, what time was it when this image was taken, like we've talked about a couple of times, the accession number that ties a study together, what the institution name was where something was acquired, the patient's name, the patient's ID, the patient's birth date, patient's sex, all of those basic demographic information, bits of information. So much as I can take a set of digital photographs and with my software, with the software that I use to organize them, I can group them into folders based on the time and the date that they were taken. You can also take a whole entire folder of DICOM objects and organize them into this hierarchy based on the metadata that's contained within those images. And so this is the basic DICOM metadata structure. At the top level, you have a patient. Each patient then can have multiple studies. Each study is made up of multiple image series. And then finally, when you get down here, you have an individual image instance. And then you can see here that this particular exam, as it's diagrammed, has 2 series, but the instances are still numbered sequentially there. So the DICOM viewers that you have will take any set of DICOM objects and organize them into this hierarchy based on the metadata that's encoded within the images. So the ultrasound machine has all of the images now, but we need to transfer those into the PACS. And the basics of any DICOM operation are 3 things that each side needs to know about each other. They need to know they're sending AE title, which for the ultrasound machine, its sending AE title is US machine. Its IP address is indicated here for the ultrasound machine, and the port of that it's going to use is 104, which is the standard DICOM port. So over here, you can see that we have the same 3 pieces of information listed for the PACS. These 3 pieces of information need to be entered into the ultrasound machine before it's able to send, and the PACS, in order to trust the images that come from the ultrasound machine, also needs to have these 3 parameters specified. If most modern PACS systems are configured such that if the sending network entity doesn't match what's expected, that it won't accept those images as a basic security operation. So we've now sent our images from the ultrasound machine back into the PACS, and they're being stored. The next thing is that the technologist goes to the radiology information system and completes the exam. So this gives us another timestamp to say when the exam has been completed. If the exam required any kind of if the exam included any kind of contrast, that will be indicated in the RIS and then communicated on in this order message that we're putting together. Who the performing technologist was, if the technologist got any additional history while they were talking to the patient, all of those things are going to be entered into the radiology information system, which will spit those out in a new HL7 order message. So that HL7 order message is again going to go to the same downstream systems in radiology. Here our PACS system is going to receive this, our voice recognition system, and then also our critical results system. In the PACS, this is actually the trigger that we use in our institution for changing an exam into what we call completed status. Once it's in completed status, it's going to show up on the radiologist work list for them to read. So here you can see that I'm here dictating and I'm looking at Rex's images. I'm using my voice recognition system. And so the voice recognition system is going to then compile all of the report text that I put together, the exam status, whether it's going to be a preliminary or a final report, the dictating radiologist, the accession number, and several other pieces of information into an HL7 ORU message or a result message. This is spit out by the voice recognition system that goes through the interface engine and goes over to the radiology information system, or the RIS. This is where it's going to live. The RIS turns around, and once it gets a finalized report, it sends that final report back out to the other downstream systems. We do keep copies of all of our reports in our PAC system, so they're readily available for comparison purposes. And you can see the final result message is going out to our health information exchange, so it'll be available for doctors both inside and outside of our institution. And then it also goes into the EMR and finally gets captured by our critical results system. We use the critical results system also to provide peer reviews, so it's important to have results there as well. So this is an example of an HL7 report message. You can see here that, again, we have our message header segment, and you can see that the message type is set to ORU. We still have our familiar PID and PV1 segments. Our observation request, again, references the same accession number that we saw before. And you can see here now that we have these additional OBX fields. So you can see here that I'm listed as the doctor who has done the interpretation, and my report is here inside the OBX segment number 2. And then there's a couple of additional fields. In this particular system, it parses out the impression separately. So this last OBX segment, or OBX4, says gallstones without acute cholecystitis, which was the impression for Rex's ultrasound. This is another zoomed up view. Again, you can see that in the first OBX, this assigns me as the responsible provider. This is the report text, a little segment here to indicate that it was transcribed by our dictation system, and then finally the impression. Before Rex leaves the hospital, he stops by the film loan and would like to have a copy of his images to take back to his doctor. So the CD burner in the film loan department performs a query retrieve operation. Again, the query retrieve operation is governed by the AE title, port, and IP address, just like the sending operation that was performed by the ultrasound machine. This is another DICOM operation, and you can query things either at the patient level, the study level, or the series level. So wanted to talk briefly, now that we've kind of gone through the end-to-end workflow for the radiology department, I wanted to talk briefly about IHE, or integrating the healthcare enterprise. DICOM and HL7, more HL7 than DICOM, are fairly loosely organized standards. And so what IHE aims to do is to put together existing standards into so-called recipes or guidelines. Those recipes specify how to use the standards in the best possible way so that things can be more consistent across enterprises and across multiple vendors. A recipe is called an integration profile in IHE parlance. So that's what you'll hear people talk about, are integration profiles. So the integration profile we've been talking about today is called scheduled workflow. There are a couple of different papers in radiographics that give more detail if you'd like to follow up for more information. So with that, we send Rex out of the hospital, healthy and happy, knowing that he doesn't need to have a cholecystectomy. If you are interested in learning more, I thought I would point out a couple of free open source tools that you can use. If you have a Mac, I know Cyrix is a great DICOM viewer, and also you can use it to view DICOM metadata. You can use it to edit DICOM metadata, and it can be a great tool for self-discovery. The DCM for Che or DICOM for Che tools are freely available Java utilities that you can use on the command line. You can use this to do things like dump the DICOM metadata from a DICOM object to a text file or to an XML file. You can also use this to do things like send DICOM objects from your local computer into an archive using those the AE title, port, and the IP address like we've talked about. And then finally, remember in the center of the diagram, the interface engine, there's an open source project that's also a product called Mirth Connect. that is an open source interface engine that you can download and play with on your computer. And then in addition to downloading Osirix, even if you don't want to download Osirix, they have quite a few freely available DICOM data sets so that you can start to have a little bit of data to play around with. It's not patient data. With that comes the end of my presentation. I hope it's been helpful, and please feel free to leave me some comments if you'd like to see more or like to hear more. Thanks.